Hi, I'm Alex. I am a machine learning architect at Slingshot Aerospace. And yeah, today I'm talking about RL for spaceflight. A little bit about, there we go, Slingshot. We have a couple different areas of pursuit that we're looking at. We are focusing on classifying individual spacecraft, things like maneuver detection and pattern of life. We're also looking at interactions of spacecraft, detecting anomalous behavior in satellite constellations or interesting behavior. And then the stuff that I'm going to talk about today, which is the reinforcement learning. All the stuff that we do is using AnyScale and Ray. We use AnyScale workspaces for remote development, for on-demand Ray clusters. We use Ray data to process huge amounts of satellite data. And we use RLlib heavily for distributed training for our reinforcement learning agents. So the orbital environment is complex, and it's getting more complex every year with more and more satellites being launched. There are a lot of things you need to take into consideration when trying to control a spacecraft. So there's things like there's atmosphere and weather. There are different ground stations that you may need to communicate with at different times, different types of signal patterns depending on your different antennas, what you may be trying to do, and you may have different mission objectives that you want to achieve at different times. And so there are existing methods for optimal control of spacecraft, but many of them lack the sort of contextual understanding and particularly the temporal understanding of the environment. And so that's kind of where RL really can shine. So we are building what we are calling the our intelligent behavior and intent system, so IBIS, where we have RL agents that are controlling the spacecraft with the knowledge of these different constraints that may be imposed, or different types of objectives that may want to be achieved. So in building this system, there are a few challenges that we want to overcome. So one is we need a system that is real. We need to use simulated data. Currently our RL agents are designed to exist within a physics simulation. So we need simulated data for training, but we also, ultimately they will be used within a simulated system, whether that's for training or for mission design or analysis. And so there are lots of different ways to simulate the space environment, and we need to be able to kind of capture many of them in our training. It needs to be interoperable in that we need to be able to kind of swap out different types of simulation engines. If we have a customer that says, we want you to use ours, and we don't want yours, or we have this proprietary one that we don't want to share. And so it needs to be very modular in that way. And then it needs to be scalable. We can have huge action spaces for our RL training. And so we really need to be able to scale it up to make the most of our cloud ecosystem. And so that's really where the Ray and RLlib has been really, really great for us. More specifically, we need simulation. We need to be able to train on simulations that are multi-fidelity because we don't know necessarily what the environments we'll be deploying into will be and what fidelity those systems will be. It needs to be multi-agent. So if we train with N agents, we need to have that be generalizable to having M counterparties. We really want to enable fast iteration so we can try out lots of different things. So, for example, we don't want to have to rebuild something if we want to go into a different simulation environment. We want it to be highly modular so we can swap them out quickly. Then finally, like I mentioned before, the distributed training lets us do all of this in a time frame that allows for experimentation and improvement. So this is just a chart that we have to show the benefits that we got with RLlib when we first started. So on the y-axis, we have the frames per second that we got with our training. And on the x-axis, the number of cores that we used, where the blue represents our local training. The yellow is kind of a dedicated machine that we had that had 40 cores. And then with Ray and RLlib, we can kind of scale up to as many as we want to using any scale. And we see a huge improvement in the number of frames per second that we can do, which really kind of takes our training to the next level. It lets us do so much more. So I want to talk a little bit about our gym architecture and how that sort of enabled this modular training that I was talking about earlier. So this is sort of the traditional RL gym architecture, where you have this feedback loop of environments providing observations and rewards and receiving actions back in turn. But one of the limitations of this is it tightly couples the environment and the agent and the gym, where if we wanted to swap out the environment for a different one, for example, if we wanted to use a different simulation engine, we would have to have a separate gym to do that. And that was not something that was desirable for us. It also, well, I'll move on. So we have sort of created this architecture where we have environment outputs that are interpreted by our sort of observation and reward providers. And the agent actually produces intents, which can then be translated by the action translators. And all of that goes into a simulation connector, which is essentially just an API that can be implemented by any simulation environment. So if we wanted to swap out a simulation environment, we can just plug it in as just another instance of a simulation connector. And the agent, the observation providers, the action translators, none of them need to know the difference. Another thing to mention here is that all of this is serializable and configurable. So a scenario that we run can be completely defined through a JSON configuration. So swapping out any of these different pieces is just a matter of changing a configuration file to use a different instance of any of these things. And so to demonstrate this, I have a little demo that I want to show, which is our RL agents playing in Kerbal Space Program, which is a video game, for those of you that don't know it. We at Slingshot don't use Kerbal Space Program, but it needs to be said. But for the purpose of this demo and to show kind of really the extensibility and generalizability of this architecture, I was able to put together a simulation connector that just ran in Kerbal Space Program instead of our other proprietary simulation engine that we have spent all this time on. But so this is a particular scenario with an agent that we've trained to capture images, quality images. And so it has two main objectives, one of which is to maintain a 50-kilometer separation from its target, and then to ensure its quality imaging by kind of staying between the sun and its target, so you don't get so many shadows. The sun is essentially directly behind. And it's a little bit hard to see in this because these scenarios actually play out over a long period of time. This particular one is in the geobelt, And so that's roughly 40,000 kilometers away. And it really plays out over many, many hours, even days. So this is a small snippet from it. I can kind of show more offline. But if we can hit play, maybe. Let's see if it'll work. So this is kind of showing on the bottom the actions that are being passed in and being shown in the UI, where you can see the spacecraft responding. It is orienting itself into the right position, firing its thrusters, and then we're fast forwarding through time until it receives its next action from the RL agent on the bottom. And as it kind of goes through, we can see here it is now firing its thrusters. You can see where the sun is behind it. There's its target, which is right about 50 kilometers away. And it will sort of just sit here, maintain this position in orbit. And so the RL agent under the covers is actually defining an orbit that it wants to be in. And the action translators that I was mentioning before are sort of translating that into what the environment expects to receive and how to achieve that orbit. That is it. I will open up to questions. Would you mind coming up to the... Thanks.
So when you talk about the action translators, when you say it's trying to define an orbit, like, can you talk a little more about what that space looks like? Or is that just really hard to talk about?
No, I can try to talk about it. It's trying to define its orbit relative to the other satellite. And so it's basically if you're familiar with state vectors, which are position and velocity in orbit, it's sort of a 6-dimensional vector. That's sort of what the output is. It's a 6-dimensional vector of an orbit. I personally was more involved on the infrastructure side, so I can't speak as well to that specific definition, unfortunately. But that is what it's outputting, is this 6-dimensional vector of a target orbit. Yeah, if you don't mind.
So in that slide with the scale up, it seemed like there was a lot of variability when you scaled up. Any idea what's that from?
We suspect, that's a good question. We suspect that it was due to overhead of the actual process of distributing and how long it would take machines to spin up and spin down, because there's a lot of orchestration that's going on in the background. This chart also wasn't linear, or it was linear. It wasn't, what's the word? It was diminishing returns as we scaled up, and that was due to the cost of doing the distribution and packaging everything up and distributing it. But it was worth it.
So the first question is, how is your experience with the RL lib? First of all, and have you been using different RL tools before? And then if you migrated, how was the change and how was easy to onboard to that? And also, for the second question, when you're running the simulations, I don't know, you mentioned this simulation connectors. Are you running the simulation on the cluster, the Ray cluster, or is it some completely different systems that you have? So maybe you want to talk about that.
So for your first question, for RLlib, we've had a good experience with it so far. We have, I'm not an RL researcher, so I can't speak so well to that, but it has been really great for what we the reason why we had switched over to it was for its distributed training, and that it has delivered in that respect. We are looking forward to, there's a new version coming out that has that should support multi-agent better, and we're looking forward to that release. For your second question, if you can repeat it quickly?
Simulation where it is running.
Yes. So we actually have it. We have our own proprietary simulation, which we actually can package up and distribute with the agents, and they run on the same nodes as the agents as they're training. So if we have 600 cores, we actually have 600 simulations running, each dedicated to its own instance of training. That's also one of the reasons why we actually wanted to have it be as modular as it is, because that's not something that we will be able to do with every environment. And if we need to switch over, that could be difficult. So yes.
Question is, how do you, you have several customers that you said, and you have unique training simulation environments that you test them out. So how do you enumerate through environments? Like how do you come up with for a particular customer's use case, there is the training paradigm, so you must have a unique environment for that, right? And how do you come up with these environments, like simulation environments? It can vary between customer to customer.
Yeah, so...
and my other question is that was this whole training paradigm running on the customer's premises or on your cloud? Or how much you share? Do you share the weights with them at the end of the day, or?
Yeah, it's a good question. And I don't actually have great answers at the moment, other than to say that those are things that we're working on. So we have a simulation environment that we are using that we aim to have as general as possible, with the intent that when a customer comes to us and says, well, we have this separate one, that we could go in and do model like fine tuning with theirs and kind of take what we have learned within ours and then apply it into theirs with a small amount of training. That's something that we are looking towards. We haven't done that yet. And we're curious to see how that will work.
I guess that's the hardest one.
Yeah. And having that simulation connector, though, does give us an API of saying, like, if you have a simulation environment and it can implement this, then we can plug into it. Yeah. Do you have another question that I missed?
Yeah, I was talking about the weights.
Yeah.
Do they really ask you that if they have a data science team or something, say, you want to really consume it, and then what is?
We, at the moment, we sort of package things up into containers. We're not kind of sharing the raw model yet.
You're not sharing the weights?
No, we're not sharing the weights. Anyone else? I think we're basically over, but.
Yeah, I was just wondering if you could speak to the action translation piece a little more. And yeah, I guess what that means and how it's different from the conventional RL cycle. So the way that we use them is actually, I mentioned about there being existing optimal control methods for controlling spacecraft. And so through those translations, we can have the agents, instead of actions specifically, they can provide intents that can then be solved through optimal control. And those translators can do that sort of translation between the two.
Did you use your own Ray cluster or managed version of Ray cluster?
We So we use AnyScale, so we use a managed ray cluster through AnyScale.
Did you try to set up your own cluster or directly started using Anyscale?
We have not tried to set up our own ray cluster yet. We have been able to do everything through the AnyScale managed clusters. Yeah.
Thank you.
Okay. Well, thank you all for listening.